अरे tak isi itu itu sama salah ya bola तो आप आ जाइए पूरा इसको मिनिमाइज करता हूं ना मिनिमाइज करता हूं हां मिनिमाइज करते रहते हैं सर अपने की बात कौन ये चल रहा है तू कौन सा है जी यार इसी को अगर फॉलो कर लो जब जब ना दे जैसे बात ये सब आई प्रोग्राम चल रहा है बहुत गरम पोजीशन है तो फैनो नहीं है नहीं इससे नहीं है जिस स्थान होगा तो इस ओके हेलो अच्छा ठीक आप बोलते रहो वो लिंक नहीं दिस लिंक एंड वो जो मोबाइल लिस्ट में दोनों सेम है हां सही हां मानस से Honestly, are you able to listen me? But आप कुछ बोलिए। लिंक नहीं हो रहा। मेरे को नहीं हो रहा। आपका बात सुनना है। अच्छा, अच्छा, YouTube से। ओके, ओके। आगे। अभी सभी ज्वाइन कर रहा अभी तो हमसे हम ठीक हो रहा है तो तुम्हारा क्वेश्चन यस तो सही है तो परिचय हमने था मैं बताया कि साथ में मत से भाई आगे ये देखला सिटी का कंपनी ऐसे लाइक पर नेट नहीं এটা আছে ऐसे गेस्ट वीआईपी सीजन में आता है अपने भी आइए या तो हम এটা না এটা না আমার মিটমাস নিয়ে ও বেবি याद না বেবি সারণ মত কথা আর না সারণ না সারণ বুঝা আছে মশাল ঠিক আছে हम लोग का स्टार्ट करो वहां से ऑनलाइन मैं ऑनलाइन रेडी कर बोल रहा हूं नहीं हां यूट्यूब पे जाना पाओ मैं यूट्यूब खाली वाला सब जा पता जाओ ये बहुत करो
हेलो
हेलो सर उन्हें बोलिए
Thank you for joining.
10%.
So we are going to start with shortly.
How many you see? How many can be cut?
Dr. Clay, my voice is audible. Am I audible to you, Dr. Clay?
Yes, sorry. Yes, I can hear you.
Yeah, thank you. Thank you. Okay. Dr. Clay, and we start. Okay. So participants can already join. So we start in 1 minute 2 minutes.
Okay, so I can't hear you very clearly. Are you saying I can start?
No, we'll start. Wait for some time. We'll start. Just 2 minutes.
Participant will come on the.
That full on.
So let's start. So this is going to be the last tutorial session and the last session also, you can say, before the electric session. Okay, so thank you, Dr. Lee, for your nice tutorial session that you have taken in the last 4 days. So this is going to be the last day for your session. So I think hopefully you have enjoyed also the sessions, different sessions, and students also have enjoyed. Okay, and personally also I have seen lectures that I want to see because I was having some lectures, so I could not attend all the tutorials, but I have attended a few where you have shown how to do the design, design the motors. Okay, so very good that we have learned the ANSYS software. So this is going to last session. So already you've been introduced so many times, but let me as a formal, I can just introduce a little bit. Okay, then we can start the session. Okay. So now we have the Dr. J with us. He has received D degree in electrical and automation from Silchar University, Science and Technology, China, 2014. Any degree in electrical engineering from US, Sydney, Australia, 2017. He has already completed his PhD degree from Sydney 2022. And he's currently working at UNSW as a postdoctoral research associate. So his research includes design and analysis of point magnetic high-speed motor drives, multi-phase modeling, and parametric optimization. So over to you, sir. So students, please be attentive and take advantage of the session.
Even in
Thank you, sir.
mobile also.
Over to you, sir.
You can log in mobile also.
Okay, thank you so much. Thanks for the warm welcoming, and I want to say a big congratulations to everyone. This is the last session. Okay, so finally we're going to complete this course. So congratulations to you. And because this is the last session, so let's do this final tutorial in a, relaxed and happy mood. Okay, so please feel free to interrupt me at any time. Okay, if you have any question, if you want to talk with me, yeah. Now let's start. I'll start sharing my screen. Oh, please okay, yes, I got it. Thank you. Okay, so welcome everyone. Welcome to the last session of the course Advanced Permanent Magnet Machine Drive Technologies for Transport, Electrification and Renewable Energy. Okay, thanks for the support from GIAN, and also thanks for the support and organization by NIT. Thank you so much. Okay, now let's start. Okay, so this is the last tutorial. Okay, so in yesterday's tutorial, we have learned how to use FE software to do transient magnetic analysis. Okay, so today I'm going to continue the Simulink workshop, and also I will introduce a little bit about optimizations. Okay. Okay, from yesterday's tutorial, we learned how to build a transient FE model of a PMSM, and also what kind of result, the performance we can get from such a model, right? We can plot the field report, the flux line, the flux density distribution, also the magnetic vectors, right? We can also get the torque, average torque, peak to peak. We can calculate the inductances. We can see the flux linkages, wiring with time, and the rotor position and current. Okay, we can also get the losses, the efficiency, power factor, all the fundamental performances of an electric machine. right? Okay, so it is a very powerful tool. So I hope you learn something from this tutorial and workshop, right? In the future, if you have any problem with using ANSYS or FEA, please feel free to send me an email. We can discuss about that. So look forward to working with you guys. Okay. And most importantly, we built this complete FEA model of the Prius motor, and we got its LD, LQ, and flux linkage, right? And also from yesterday's tutorial, we learned that in Simulink, the motor model is actually just the equivalent circuit, the torque equation, and the motor motion equations, right? So if you want to do drive of a PMSM machine, PMSM, okay, so you need to at least know its pole pair, okay, the magnet flux linkage, LD, LQ, right? And also we need to know its inertia, the damping ratio, and the friction, okay? So if you have a prototype, like a real machine, you can definitely measure these values. But in reality, at most of the time, when you just started to design an electric machine, you don't have the prototype, right? We only have the FEA model. So you can build the FEA model and get these fundamental parameters of the machine, okay? And then you can work on the drive. So your project can go parallel. So the team can work on the motor design, another team can work on the motor drive in parallel, right? So this is the advantage of using FEA in motor drive and motor design, okay? And in yesterday's tutorial and lecture, we have learned the FOC drive, okay? How to implement the flux-oriented control on an IPMSM machine, okay? So this is the control block diagram, right? So it is in such a control, we want to control the speed of a particular IPMSM. So we give it a speed reference. And also from the encoder, we can know the real-time speed of the machine. Then we get the speed error, okay, process it with the speed PI controller. The output can be either torque, RM reference, or IQ reference, okay? Then based on the output of the speed controller and the real-time speed, we need to decide which control trajectory we want to follow, okay? Whether it is MTPA, maximum torque per ampere, flux weakening, or maximum torque per voltage, okay? Per volt, not per voltage, sorry. All right, so how do we know which trajectory we need to select? Okay, Professor Data has introduced this in her lecture, right? So we need to calculate the base speed, the crossover speed, and also the critical speed of that machine. The equations were provided in the lecture, okay? So basically, the base speed is when your MTPA trajectory, the voltage limit intersects as a point, intersect with the current limit, okay? Meaning, if our machine is operating at a speed lower than the base speed, you can apply the MTPA trajectory, okay? So you can use any IDIQ on this trajectory and it won't exceed the current or voltage limit, right? Crossover speed is when the MTPA trajectory and the voltage limit overlap with each other at the zero ID point, okay? This means, okay, whenever you apply MTPA at this speed and any speed higher than the crossover speed, the ID and IQ will induce a voltage that exceeds the voltage limit. So we need to operate the machine following the voltage limit line. So this is the crossover speed. And in between base speed and crossover, we need also the current to decide the load, and not also the current to decide which trajectory we want to follow. Okay, for example, at this speed, when we just start up the machine, when the machine is operating at a no load or low load condition, at the beginning, we can use MTPA. Okay, but when it goes to this point, okay, the MTPA IDIQ will induce a voltage that is equal to the maximum voltage limit. Then from this point, we need to follow the voltage limit. Okay, so this is how we decide which trajectory we need to use. And this control diagram, this control block should be located here, okay, right after the speed controller. And using these trajectories, we can calculate the ID and IQ required to provide the torque to accelerate or deaccelerate the speed of the machine to the designated one, okay? And after that, we have the IQ and ID controller, PI controller. We need to do the DQ transformation, reverse DQ transformation to alpha and beta axis, okay? And then we can get V alpha and V beta. After we get V alpha, V beta, we need to apply the SV PWM, right? The space vector PWM to generate the duty cycle for each switch. Okay, in our inverter, we have 6 switches. Okay, we need to use SV PWM to generate the duty cycle for each switch. And this part of knowledge is also covered in Professor Datta's lecture. Okay. Okay, all right. So this is a brief review of the FOC control. Okay. Another knowledge point I want to emphasize to you is that when we see FOC control, we are actually referring to this part of the control from ID and IQ. So this is the FOC control, okay? Meaning we are using ID and IQ to control the field, the torque, and the speed of the machine, okay? The first part is the speed controller. No matter what control method you're using, you need the speed controller, okay? So see for this one, Professor Datta introduced the direct torque control. For this one, we also need the speed controller, okay? After that, we use the torque and the flux to control the machine and the inverter to generate the duty cycle, the gate signal of each of the switch in the inverter, right? So this is DTFC control. All right. Now, let's go to the Simulink model. Okay, I have uploaded this model to the shared Google Drive. So you may download it to your own computer and explore. I hope you have tried using this model. Okay, this is the most basic and fundamental, and also you can say the most classical FOC control. Okay, I did my best to make it look neat. Okay, and you can see all the parameters are properly named, so you can know inside each block what's inside each of this block. Okay, so and yesterday we introduced how we construct the hardware part. Okay, so we have this 3-phase inverter, we have this PMSM, and inside it is actually the DQ equivalent circuit, the torque equation, and the motion equations. And to build this, you need LDLQ, RS, flux linkage, and the mechanical parameters, right? The input and output of this block is, the input is just the gate signal, the duty cycles. The output is 3-phase current, DC voltage, and encoder position, right? We don't always know the torque of the machine, but we can estimate this one using the parameters and IAIB IC. Okay, so after IAIB IC, we need to transform them to ID and IQ. And also a very important part is to decouple ID and IQ, okay, to do a decoupling. Okay, so why we need to do the decoupling? Do you still remember why we need to do the decoupling? Okay, so this is also provided in Professor Datta's lecture. Okay, so we want to decouple IQ in VD and ID in VQ, okay, to make the current controller faster. So this is the diagram and the equation. If you open it in our Simulink model, you will see the same equations, okay? So this is built exactly as the block diagram and the equation indicate, okay? So they are completely the same as the equation and the block diagram. Right, so after we do the decouple, we have the VSD and VSQ to be used in the control, okay? So let's talk a little bit about the control, right? So you can compare the Simulink control model with our control diagram showing here, okay? Again, they are the same, okay? So at the beginning, we have our reference speed. For example, in this case, we want the machine to operate at 1000 RPM, okay? And this is the speed measured from, the electric machine, okay? And we get the speed error, it passes through the first PI controller, which is a speed controller. The output of this PI controller can be either torque or IM or IQ, okay? In this case, we are using this PI controller, the speed controller, to generate IQ reference, okay? Then using the IQ reference, and in this model, we assume the machine only operates at MTPA region, okay? So this is a place you use the equation for MTPA to calculate the ID reference. So this is how we get the ID reference, okay? And after we get ID and IQ reference, okay, we need to apply them in the next two current controller, current PI controller, okay? So this one and this one. And then we can get our VSD and VSQ, okay? So actually the decoupling should be after the control. So we get VSD and VSQ, we do the decoupling, we get VS, the decoupled VSD and VSQ, okay? And after we get the VSD, VSQ, we go to the SV PWM generator, okay? I hope you still remember what's inside the SV PWM generator, okay? So, so for an inverter with 6 switches, we can have 8 combinations, okay? And we only need to, and then we can draw them in this vector plot, okay? So a full circle, 360 degree, means 1 full electric period, okay? So we need to operate the 6 switches, okay, to generate a circle, okay? Because a circle in the alpha beta reference frame is a sinusoidal wave in the time frame, okay? So which is the voltage wiring with the current, okay? With the time, sorry, yeah? And based on the theta angle, okay, in the alpha beta reference frame, we can decide, okay, currently the motor is operating in which sector, and in each sector, which switches we need to control, okay? And if you go to this block, you will see the same thing. So we get VSD and VSQ, and we do the alpha beta transformation to get V alpha, V beta, and then from that, we calculate the vector number and the angle, okay? Then using the vector number and the angle, we decide, okay, which switch we need to turn on, which switch we need to turn off, and what is the duty cycle. There is a matrix for you to calculate the duty cycle for each switch on the different condition, okay, for each different sector and vector angle, Okay, so this is how we build the S3 PWM generator, and the output will be duty cycles. Okay, duty cycle for each switch. And the duty cycle for each switch will just go directly to the inverter, and that controls the PMSM. Okay, and again, we can, in the next cycle, in the next control cycle, we will get the new IA, IB, IC, VDC, and rotor position. And they just repeat this control cycle, and then we can complete the FOC control. Okay, now let's look at the result. Compelling, open the diagram. Okay, so we are controlling the machine to accelerate from 0 to 1000 RPM. Okay, so you can see this is how ID follows ID reference. So how ID follows ID reference is controlled by the ID PI controller. And this is controlled by the IQ PI controller. Okay, this is the speed. The orange one is the speed reference. The blue one is the encoder measured motor speed. The yellow one is actually the speed estimated by sliding mode observer. We won't talk about the SMO controller, but it is built inside this model for you to explore. Okay, and Professor Data has covered SMO. Okay, but at the basic level. So this part of knowledge is for you to explore at your own time. And if you have any question, you can send me an email. We can discuss about that. Okay, so you can see when we change the speed, okay, when we change the speed reference, the motor's following the speed reference very well. Okay, in control, we don't want the speed to have speed, current, everything. We don't like the overshoot. Okay, because at the full speed and the maximum torque condition, maximum load condition, that may exceed the motor rating. So we always design the controller so that the machine will operate at a under-damped condition. Okay, so we like this type of slow rising, but not very slow. You can see the machine can accelerate from minus 1000 RPM to 1000 RPM within 0.2 seconds. So it is already very quick enough. This is the curve of the torque. Okay, you can see when we change the speed reference, controllers trying to get a high torque, the maximum torque to accelerate the machine to the designated speed. Okay, and this is the three-phase current. This is the real-time rotor position. Okay, let's stop it here. And you can do more things using this model. For example, you can also change the load here. Okay, so you can change the load here. You can change the speed and see how this model follows. And another very important thing, besides building this control and the motor model itself, is how to tune these three PI controllers. Okay, how to tune these three speed, current, IDIQ controllers. Okay, because for each controller, we need to set the KP and KI. Okay, so how to quickly get the value of KP and KI. Okay, I will introduce this in the next slide. But before I go to that, okay, do you have any question about the Simulink model? Have anyone tried using it? Do you have any question about it? Nope. Okay, that's all right. Now let's see how should we tune the PI controllers. Okay. Oh, sorry. So the most widely used and the classic method to tune PI controller is called the pole placement method. Okay, so I won't go too deep into the series, the control series, the transfer function, the plant model of the pole placement method. Okay, because we are engineers, so you don't have to understand it. It is good if you can understand it, but most important thing is you need to know how to use it. So in this tutorial, I will only briefly introduce the series, and most importantly is how should we use this pole placement method to calculate KP and KI. Okay, so in this case, we are using the ID and IQ controller as an example. Okay, so first let's see the series of pole placement. Okay, so basically is for every control system, you need to know its transfer function. You can also call it the plant model. Okay, and because we are trying to build this model in Simulink, and Simulink is discrete, so we need to discretize the plant model, right? So after we build the transfer function, we discretize the plant model. The next thing is to write the PI control equation and also discretize the controller model. Then we combine the discrete plant and controller model. We can get the characteristic polynomial for the system. Okay, and to achieve the control performance that we want, you need to set the characteristic polynomial for the system equal to the characteristic polynomial of the required performance. All right. If you do this, you will get these equations, the coefficient alpha, alpha 1 and alpha 2. Okay, so this is the psi, the damping ratio of the control system. Okay, omega represents the angular speed. Okay, if it is for the speed controller, this should be your mechanical angular speed in radian per second. If this is for the ID and IQ controller, it should be, okay, your electric angular speed. Okay, and TS is the sampling period. Okay, and also we have another coefficient A1 and B1. A1 equals to TS minus TM divided by TM. Okay, and what is TS? What is TM? TS is the sampling period of our controller, and TM is the time constant of the first order system. Okay, in for PI controller, we only consider the first order system. Okay, so TM is the time constant of the first order system. For ID and IQ controller, TM equals to L inductance divided by the phase resistance. If it's for ID controller, you need to use LD. If it's for IQ controller, you need to use LQ. Okay, and B1 equals to Km times TS divided by TM. Okay, Km is the first order gain, and that equals to, for the ID and IQ controller, that equals to 1 divided by RS, the phase resistance. Okay, then using alpha 1, alpha 2, A1 and A2, we can get Q0 and Q1. Okay, so these are the equations to calculate the value of Q0 and Q1. And then using Q0, Q1, KP, using Q, and then we can get the value of the proportional gain, KP, the proportional control coefficient. So KP equals to Q0 and KI equals to Q1 plus KP divided by TS. Okay, so in the shared drive, in the Google Drive I shared with you, in the MATLAB file, you will find the MATLAB code, okay, applying these equations to calculate KP and KI for the ID and IQ controller of the Prius IPMSM motor. Okay, they are exactly the same. Okay, I can probably show you the code. Okay. So if you can see this, maybe it's probably a bit small. Okay. So it starts from here. Okay. So this psi is the damping ratio. Omega n is the electric angular speed. Actually, not electric angular speed. I should not say it's electric angular speed because it is 2 pi f. F is the bandwidth of the current controller. Okay, it is actually the control frequency. Okay, then Km is our first order gain. Tm is the time constant. Okay, of the first order system. For ID controller, it is LD divided by RS. For LQ controller, for IQ controller, it is LQ divided by RS. And this is the equations to calculate B1 and A1, alpha 1, alpha 2, Q0, Q1. And this is equation to get the KP coefficient and KI coefficient. Okay, the value of KP and KI for the ID controller. The value of KP and KI for the IQ controller. Okay, so if you want to run this Simulink model, you need to run this MATLAB file first. Okay, because this will calculate all the essential parameters you need to use in your Simulink model. Okay, if you click this PI controller, you can see the value we calculated in the MATLAB file is directly applied here, KP and KI, the value we calculated. Okay, and if you see here, the KID and KPD, which is the KP and KI for the ID controller, made the IQ following the ID reference very well, right? And also we have IQ following IQ reference very well, okay? So this is how you use the pole placement method to calculate the KP and KI, okay, to be applied in your current controllers. Okay. Okay, so up to here, do you have any questions about this? This is the very classic method, okay, to tune the PI controller. Classic, but useful. No? Okay. We don't have any question, then let's try using this model and try change the load condition. And let's see how the motor will respond to a load change. Okay, so in this case, we need to, let's give the motor a constant speed reference and let's run the model. Okay, so you can see now this ID is following ID reference, IQ is following IQ reference, speed increasing from 0 to 1000. And when it reaches the designated speed, our torque will gradually drop to very close to 0. Okay, so this is a place we change the load we apply to the PMSM model. Okay. So after we apply an additional load, you can see the speed dropped, okay? And because we applied an additional load, okay? So, and also now the controller is trying to get a higher current amplitude to increase the load to compensate the mechanical load we added to the machine, okay? So there will be a sudden speed drop and then the speed will gradually go up to the reference value. If you think it is increasing too slow, then you need to tune the speed controller Okay. Oh, not here. So we can increase KP and KI to make the machine go back to the steady state faster. Okay. Now let's try increase the load again. So after we further increase the load, the current also increase. Okay, the speed drop again, and then the controller is trying to get a higher current, higher torque to accelerate the machine back to the speed reference. Okay. Okay. So on this plot, it appears the speed of the machine is going back to the reference one very slowly, but the real time frame, it's only 2 seconds. Okay, so from here to here, that's 2 seconds. So the machine is actually accelerating back to the reference speed in a reasonable range of time. Okay, but if you still feel it's too slow, you can further increase the speed controller values. Okay. Okay. Like I said, this model is also built with the sliding mode observer. Okay, so this is the sensorless position estimation algorithm. Okay, Professor Data has covered the basic knowledge about SMO. You can explore this block later in your own time, and you can also switch to sensorless using SMO. Just click here, it will go switch to SMO controller. Okay, so this is basically what's built inside this model. And yeah, do you have any question about the Simulink model? Okay, using a field-oriented control. Nope. Okay. If there's no question about field-oriented control, then let's go to the last part, okay, about optimization. So how should we do a machine optimization using the optimization algorithms? Okay. All right. Okay. So the two most commonly used multi-objective optimization algorithm is the particle swarm algorithm and the genetic algorithm. Okay. Professor Data has introduced both algorithm in her lecture. Okay. But let's go through them together with more technical details. Okay. The first one is called particle swarm algorithm. Okay. It is inspired by the swarming behavior of biological populations, such as bees and ants. Okay, so the theory is, okay, so let's say we have a group of bees, and when they try to go out and hunt to find flowers and honeys, they will spread themselves across the whole field. Okay, and they will communicate with each other. Okay, to find the area with the most flower and most honey. Okay, so that is a simple explanation of the particle swarm algorithm. And you can also see from this figure. Okay, so this is kind of the field, and we are asking the particle swarm to find the lowest point, which is here. Okay, so at the beginning, they are spread out evenly across the whole field, right? And each of them will evaluate its current location, okay? And they will communicate with each other to decide where they go, okay? How to decide where they go? They need to consider a few factors, okay? The factors are their current motion influence, the particle memory influence, and the swarm influence. The current motion influence is, let's say previously we have this bee at this location, okay? Then it moved from the previous location to this location, right? So it has kind of an inertia to let it still go to this direction, right? Then the particle memory influence, okay, is like this bee remembers every place it has went to, okay? Based on the area it has went to, it would decide, okay, approximately this direction has the most flower. And swarm influence is the result this bee can gather from all other bees, okay? So it's a general trend, okay? So that's the knowledge of all of the particle swarms. Then you combine these three vectors together, you will get the new movement vector. So it knows, okay, considering all the factors, I should go this way. Eventually, they will all approach to the optimum point, which is the lowest point, okay? So that is how particle swarm works. Particle swarm, comparing to the genetic algorithm, it converges faster, meaning it can find the global optimum faster. But it has a problem that is, it tends to be trapped in a suboptimum state, okay? Such as you can see these particles, they are trapped at a local optimum design, okay? So they didn't find optimum one, okay? So sometimes maybe if you have a design field that is very complex, all the particles may trap at the suboptimum state. So it cannot find the real global optimum design, okay? At USW, in our research group, we are using the genetic algorithm. It's also called the non-dominant resulting genetic algorithm, the second generation, okay? This is inspired by the process of natural selection. And I believe Professor Data has introduced about this. So basically what it does is, so it uses the parameters of an electrical machine as the DNA, okay? So like what we did to the FE model, we know for a real FE model, the motor model, the geometry, the material property, the current we apply to the machine, they can all be represented using these variables, okay? So each variable represents a segment of information stored in the DNA of the machine, okay? So then let's say we have 100 designs, so meaning we have a population with 100 design points. We evaluate all these 100 designs, we get their performances, okay? If let's say we're only considering the cost, and also the loss. So we want to get the design with the minimum loss and the minimum cost, right? That means this corner is the best. So let's say this is the evaluation result, and how to decide which design is the best, okay? So we use the non-dominant resulting algorithm to find the best designs. I'll talk about this later, okay? But after we select the best ones from the current population, we'll use the best ones to do crossover and mutation. Crossover is like exchange your genetic information, okay? For an electro machine, that is exchange the rotor or stator, geometric parameter, and current density, and other variables. Mutation is like we randomly select a few parents, and we randomly change a few number of its parameters, okay? And then we generate a new population, and we circle, and we repeat this process until we get the optimum design, okay? Now let's talk about the algorithms, the non-dominant sorting algorithm and the crowd distance algorithm a little bit more, okay? Professor Data has introduced about the overall process. So it's basically like what I said, we have the population, we evaluate its performance, okay? If it's the first generation, then you don't need to do this process. We just sort it, further sort it using the crowded list comparison, okay? We get the sorted generation, we get the new generation, okay? The sorted population and the rejected ones. So we only took the best ones. We use the best designs, pass it through the crossover and mutation operator, generate the next design, repeat this process, okay? If it is the second generation and any other generation other than the second one, we need to compare all the designs of this generation and all the previous generations to select the real optimum designs, okay? Now, how does the non-dominant sorting works, okay? So this is how the non-dominant sorting works, okay? So these are the designs we get from one evaluation, okay? So what does it mean, like non-dominated or dominated, okay? So it means, let's say if we use this design as an example, okay, so we draw two lines that are perpendicular to each other. Then every other point sitting in this area dominates Qi, okay? So this one dominates Qi. And also in the MATLAB or Python code, we see Q1 is dominated by another design, okay? And Qi also dominates, okay, any design point sits in this area is or are dominated by this design, okay? So we see these two designs are dominated by Qi, okay? Any design that is not dominated by other designs, okay, is called will be classified into the first rank, okay, which is F1. Any design point that is dominated by only one other design goes to F2, dominated by two other design goes to F3, and this rank continues, okay? So ideally, we only select the best ones in F1, the group F1, okay? But at the beginning, in the first few generations, we probably won't get enough candidates in the group F1. So at that time, we'll consider a few other designs in F2 or F3, okay? But as the optimization continues, at the end, most of the design will concentrate near the Pareto front, which is the group F line, the line, okay, the line of group F1, okay? And at this time, we need to further apply the crowd distance algorithm to select the best ones, okay? But at this time, it's not comparing whose performance is better, but who's more unique, okay? Because let's see, at the 20th generation, we have 70 candidates on this line, but we only want 50 candidates to generate the new generation. Okay, so how can we select the 50 out of the 70? They all have similar performance, Okay, they are all in group F1. So in this case, we need to calculate the crawl distance, or sometimes you can call it crawl area of each candidate. The crawl distance is, if we use QI, I can use QI as an example. The crawl distance is you draw a rectangle around Q1, and these 2 points need to overlap with the two. So you draw a rectangular based on Q1 and the other 2 candidates that are next to it. The length of this rectangle is called the crawl distance. Okay. Designs that has a larger crawl distance means this design is more unique. So we want to keep this design. Okay. In some other case, we may have 2 design points very close to each other. Okay, let's say we have this, we also have a design point here. Then this design, you can see it has a crawl distance much smaller than QI, right? And because this design is very close to this one, okay, their performance are similar. You don't want to evaluate designs that are very similar to each other, okay? That's kind of like repeating the evaluation job for candidates that are very close or similar to each other. We want to ensure the diversity of the population. Okay, so we want to pick the unique ones. This can make our optimization more efficient. So this is how the non-dominated sorting and crawl distance works. The non-dominated sorting help us to select the best designs. Crawl distance help us to ensure the diversity of the new population, and also it helps to improve the optimization efficiency. So this is how this works, okay? And after that, we will have the sorted population, okay? So you can see basically here, this is a whole population of one generation. We will have group F1, which is this line, group F2, which is this line, group F3, which is this line. And we only want to get the best first half. Okay, so we select the best first half and pass it through the comparison operator. F1 and F2 has no problem, okay? But in F3, okay, we need to select the unique ones. We need to select the unique ones sitting in the group F3, okay, and reject the rest ones to ensure the diversity and efficiency. So now the new sorted population will include all design points in F1, all design points in F2, and the unique ones in F3. The rest will be rejected. We use the sorted population, go through the crossover operator and the mutation operator, okay, to generate the children's. And that will be our new generation. And then we repeat this cycle until we get the Pareto front, which is a global optimum. And we select the global optimum design. From the Pareto front. So this is basically how the algorithm works, okay? Do you have any question about this part? Any question about the non-dominated sorting or the crawl distance? Or if you have any question about the previous step, please let me know. Do you have any question about the genetic algorithm? No? Okay, then if you don't have question about that, I want to show you a few other things, a few other functions of the, oh, my answer is frozen. I can't open it. All right. Okay. Let me close it and reopen it to show you some result of FEA. Okay. Okay, so please give me a few minutes to solve the technical problem. In the meantime, if you have any question, you can organize your question and send it through the chat window, and I will help you to solve it. Any question about the pole placement method to tune the PI controller or the optimization algorithm, please let me know. Okay, so let me solve the technical problem. I'm sorry for that. Okay, I got one question asking which type of method you have adopted for tuning the algorithm parameters. Okay, so what algorithm parameter are you referring to? Which algorithm parameter are you referring to? Sorry, I can't hear you clearly. Okay, let me go back to the. Do you want me to open the Simulink or the PowerPoint to answer your question? So is it a parameter in the Simulink model, or is it a parameter in the optimization algorithm? I guess it's for the I guess it is a PI controller. Is it a question about the PI controller? Okay, like in PSO cognitive. Okay, I can't, sorry. Yes. Listen, how can we choose appropriate value? Oh, you mean in particle swarm, the optimization algorithm? Okay. All right. Let me go back to the part of the optimization algorithm. I'll start sharing my screen again. Okay. So you're asking what weight factors we should use here, right? So you can see here's recommended factors you need to consider for inertia, self-confidence, and swarm confidence. There's no standard way of choosing these factors. So there's no simple equation that can help you to calculate all of this. I would say I never use particle swarm for optimizations of my own motor. Okay, but I have talk with someone. I met someone who used particle swarm to optimize machine in conferences. Okay, so I guess it's first it depends on the application. Okay, so what design, whether it's an electric machine or a transformer or the inverter you're optimizing, and also what performance are you applying which performance are you applying this algorithm to? Okay, so that really depends on the application of the algorithm, and these are only the recommended values. Okay, so these are the typical values you should select, but you should not be bounded with this range. Okay. And I always tune these factors during an optimization, because you can never, so even we always say we can use the optimization algorithm to find the optimal design, but it's in reality, it's not like that. You probably need to perform multiple optimizations to find the final global optimum. And after the first optimization, you may find, okay, the inertia factor is too big, or the self-confidence factor is too big, then you need to tune its value, okay, for the next optimization. It is really based on your experience. Okay. Yeah, but if you're using particle swarm in machine optimization, okay, feel free to send an email to me. We can talk, communicate out of this class. Okay, I'm very happy. I'll be very happy to talk with you, to communicate with you about particle swarm algorithm. Now let's see if it's still trying to open that. Okay, then let's use this time to do a survey. Okay. We have prepared a survey for this course. We are looking forward to get your feedback. Okay. Okay. Oh, this is a long one. I have sent the online survey link to the chat box. Please click it and open it to access to the survey. It is anonymous, so please tell us your true feeling about this course, the lectures and tutorials, and how we can improve. Okay. Thank you very much for answering this survey. Okay. Let me know if you have any problem opening the survey.
Is there some issue? I tried to open it. I don't know. For other participant, are you able to open it? Shatish?
Okay. If you, oh, okay.
It's saying it's not accepting the responses. So I think that is not activated. Please look into that.
Okay, let me try to solve it.
Yeah, please.
Share.
Now it's okay. Dr. Klee, it's fine now.
Okay, yeah, that's good. Thank you.
Oh,
Okay, now I finally get the software open, and sorry for that technical problem. Okay, the thing I want to show you is parametric analysis. Okay, how do we do a parametric analysis using ANSYS, using any other software, FE software? Okay, so previously we have solved this transient model for a fixed theta angle. Okay, theta angle is the angle between the current vector and the Q axis, right? And if you still, if you remember what we learned from the lecture, the MTPA is the theory of field-oriented control is like we can use the current amplitude and also the current angle to control the magnet flux, the flux linkage, and also to control the torque. And for IPM SM machine, who has both, okay, let me draw it here. So for IPM SM machine, normally we have both the magnetic torque, okay, and also the reluctance torque. Okay, the x-axis is the value of our theta angle. Or in other case, you can also represent use gamma use the Greek letter gamma. Okay, so that means we don't, for IPM SM machine, we don't always have the maximum torque when gamma equals to 0 degree, right? So sometimes we have a higher total torque. Let me change the color. If we sum the magnetic torque and the reluctant torque together, we could get a new total torque curve like this. And the maximum torque, you can get the maximum torque when your gamma angle equals to a particular value, okay? And the ID and IQ calculated using this gamma angle. Okay, sorry, this is Q, can provide you the maximum torque per ampere, right? So theoretically, this is a theory of MTPA control. We find the gamma to get the ID and IQ to get the maximum torque per ampere operating condition. You can also find that maximum torque per ampere current angle using FEA. Okay, I'm going to show you how to do that. First, I want to show you this. So when we assign current excitations to the three-phase winding, this is the current equation, which is Rmax times sine omega times T plus theta. And this theta is that current angle. I'm sorry I'm using theta sometimes and gamma, but it's the same angle I'm referring to. Okay, so we want to find the theta angle that can give us the maximum torque per ampere operating condition. How do we do that? Okay, so we need to use the parametric analysis, okay, to set up a swept analysis. Just right click on the optimetrics, add parametric analysis. Sweep definition, click add, find theta. So this is theta degree, which is meaning the value is in degree. Okay, linear steps. We want to try theta angle from 0 to, let's say, 60 degree in steps of 5 degree. Just add it here, click OK. If you go to the table, you can see we get all the theta angles we want to try. Okay, so it will solve the same model with different theta angle, okay, automatically. After you set this angle, okay, you can click OK. So that's the settings, the basic settings is done. You can also override the other parameters we define for this model. For example, if you want to do the theta parametric analysis with a different current angle, so you need to check override, change the value to the one you want to try. Okay, you can also change the speed. You can also change the pole number. Okay. And you can also let the software know what other calculation you want to know. For example, torque, for example, the losses, or the flux linkage or inductances, anything you need. And whether you want to see the field for each design point. Okay, so after you set it, just right click on it and solve. Okay, so this is the torque analysis result. You can see we get multiple torque curves for different theta angle. Okay, but if you want to get the theta angle that can give us the maximum torque per ampere, you need to calculate its average value. Changing the y-axis data to average value, you change the x-axis to theta, click apply, you will get this plot. Okay, so this is the average torque value wiring with theta. Okay, wiring with theta. Okay, and you need to remember in this case, the current amplitude is constant. So we have a constant current amplitude. The only thing we are changing is the theta angle, which is the current vector angle. Okay, so you can see when theta equals to 50, we have the maximum torque that is very close to 400 Newton meter. Okay, so this is the maximum torque of the Prius machine claimed on their report, right? So you need to not just apply the maximum current, you also need to find the theta angle that can allow the machine to operate at the maximum torque per ampere condition to get the maximum torque. Okay, so this is how you can perform a parametric analysis. Okay, in this case, I'm only showing you wiring theta, but you can also do parametric analysis of other parameters, such as the air gap. So if you still remember, we introduced how to estimate the air gap length, but that's only a theoretical analysis. That air gap may not give us the optimum performance. So you can create a variable representing the air gap and set a parametric analysis here, wiring that air gap from in a certain range, and you can know from your report which air gap gives you the optimum performance. Okay. In this case, when you do parametric analysis, you can only do that for one or two or a few parameters. Okay, but when you do an optimization using algorithm, you can actually use all design parameters as your DNA and then apply it in the optimization algorithm. Then you will get, eventually you will get the optimal design. Okay, so that's how the optimum optimization works and how the FEA parametric analysis works. Okay, thank you so much. That's all from me today, and this wraps today's tutorial, and it also wraps our course. This course is very interesting course, okay? But I hope this is not the end. This is just the end of this course. This is not the end of our relationship. I really look forward to communicate with you, talking with you about your research work, okay? So I know many of you do not work in the field of machine design or machine drive. You are yourself is an expert in the other field. So maybe someday later, I will need you to teach me, you know, knowledge and skills in your expertise. So yes, thank you so much for listening. And if you haven't completed the survey, please continue. Yep, that's all from me.
Okay, thank you, Dr. Clay, for nice talking. Okay, and like tutorial was very like you can say interactive in its own way. Okay, like you have done meticulous job in you arrange the blocks in a very good manner so that to tune the PI controller. It's very good, nice. Okay, and very thank you. And I request any participants if you have any questions. So already Dr. Clay has asked about the questions. If you have any question, then it's fine. Else we'll wind up the session. Okay, so no questions. So thank you, Dr. Clay. Thank you, Dr. Datta is here right now. Okay, thank you, your team that has like great jobs done in the last week, like complete 5 days. Okay, we have learned a lot. Okay, thank you. Okay, so over to Saikya sir.
Yes. Thank you, Amritas, for entering this session. I have now no members how I can do this given by Dr. Clay and Madam. Actually, in Silchar, we should be in class so that our can get help from your side. Dr. Clay always I said told you any problem we have faced in Simulink analysis. Okay. And Madam, we'll start our valedictory session at 3:30. We can take a rest for half an hour. After that, we will begin. Thank you, Madam.
Thank you very much. And I again request you all to please do the survey so that we can make it even better when we give it next time. So please, the participant, complete the survey. Thank you. So I'll see you again at 3:30. Thank you, Clay. In fact, I was also learning some of the things from you while you are presenting. Yeah, thanks a lot. Okay.
Thank you. Thank you all for listening. Yes, thank you all for listening to this tutorial. Okay, so it's a week of 5 days tutorial and lectures. So you did very well. Thanks for listening and thanks for your feedback. Yep.
Okay.
Okay.
When Valedictory also, valedictory function. Dr. Clay, please join at 3:30. At 3:30, there is a valedictory function here. I request you to join here. Okay, the same link will be worked. Okay. Thank you, sir. So,
Okay.
Yep.
We'll leave now and then we'll rejoin again at 3:30.
take a screenshot, madam, this way. Please hand over.
Because I don't get a lot chance talking with you. I know many of you are very talented research students or engineers. So maybe we can use this few minutes to chat. If you want to talk with me, you know, what you are doing, what is your research topic.
Okay,
You can see.
Please, you can freely discuss with Madam and Dr. Clay about your research topic, and you may get help in your research. Please freely you can ask.
You can use the chat window
Yeah.
and put your name and your research topic maybe, so that we will know what you are doing. We have talked about a lot about what we are doing, but maybe now is the time you tell us what you are doing.
Okay. Thank you, Madam. Okay, we can end up here the tutorial session as well as the technical session for this workshop. We will meet at 3:30. Thank you. Let's stop this second.
We are waiting to see your topic, research topics in the chat window.
Yes. Anybody, please come. Okay. In like your research topic, all of you, please.
At least those who are doing research, maybe not all of you are doing research. So those who are PhD students and doing some research, you can tell us what's your research topic.
All of you, please write your research topic. You may get some help from Madam and Dr. Clay.
Oh, I actually prepared a very nice wrap up for my tutorial. I forgot about that. Okay, let me see that. So it's probably a bit cheesy, but yeah. So we are living at the time of the big changes is happening. So there's an electrification is definitely one of the major trends. So there's a lot of opportunities and challenges waiting for us to solve. Okay, so it is very nice to know all of you through this course and hope we can collaborate in this field in the future. Yes. Okay, power system operation including renewable energy source. Yes, that's a very good topic.
Sanjeev.
Yep. So renewable energy source meaning including solar panel, wind turbine. So yeah, it's very similar to what we are doing at our research group, right, Professor Data? So we have many students working in the same field.
Write your research topic. which you are working, right? Wait. Setbox is right. Setbox is right.
DFIG-based wind energy conversion system interface with utility grid. Okay, now it's time I become the student. What is DFIG? Oh, doubly fed induction generator. Is it doubly fed induction generator? Yes, I guess yes. Doubly fed generator. Yep. Microgrid control techniques, application of integral and the fractional integer control on maximum power tracking and control operation of microgrid. Very interesting. Frequency stability of microgrid. Yep.
Most of the participants from energy Silchar, actually they are working on renewable energy related topics. Mainly my topic students, there are two of them are working in microgrid, Manoj Kumar Vera, so, and Alu. And others are doing frequency control. Frequency control means automatic generation control. Where of the system where all the renewable sources one by one they are considering, and model we have considered is transfer function model only. So that's why we have to learn whatever the transfer function model we have made and use for simulation. We have to learn everything and we have to simulate that type of system. Okay. So yes, we are proposing various secondary controllers like fractional model controller, utility controller, and including PI, PID, and also. You can come and see also. Okay.
You see also. Okay. Use the microphone.
Yep,
Hello.
it's very popular microgrid and power system research. In our research group also quite a lot of people are doing in microgrid and others, but we are the larger group does this power system and microgrid. We are only a small group of us do power electronics and motor drive. So yes, of course, power system microgrids are very popular everywhere.
Yep. But many microgrid does have generators.
Yes, yeah, all wind generator.
Yes. So learning the theory, principle, and fundamentals of electric machine and machine drives would also be helpful to your research about microgrid. And if you have a specific microgrid, yes. Do you have anything you want to say, Professor Dada?
No, I'm saying that it is like DFIG who are doing it you are actually doing a very similar DQ control only. The induction generator drive. It is the FOC control that we have discussed for PMFC, there is a FOC control project induction machine. So in DFC, actually, that's what is can be used. So we hope that is definitely quite similar. Then many microgrid, as we talked about in the beginning, mainly supporting generating systems with micro gas turbines or even smaller PM generators driven by engine, because not everyone can install large batteries. So that in that case also, again, we need to know this. If you work on microgrid, you need to understand actually PMSM or PMFC control. And the power electronics, yes, DC-DC converter, hydrothermal, GC of multi-area hydrothermal power system with impact of distribution, generation, the system frequency control. Frequency control is a very interesting topic, especially if you go to renewables, like if it is solar, then there is not enough system inertia. So how to create partial inertia? That's a very upcoming topic in the power system research. And that again, power electronics and controls.
Yep. I know a few graduated PhD who used to work in the same field. We had discussions about the virtual inertia. Yeah, so if you're interested, send an email to me. I may introduce you to our PhD students and you can collaborate. Yeah. And we only did the tutorial for using FEA on electric machines, but actually FEA is more frequently used in other systems like converters and inverters, because converter and inverters also generate a huge amount of heat and they have very complex EM field. So if you're working in field that involve inverter, converter, and other power electronics devices, you can also look into how you can use FEA to assist your research.
I can see Amit has a quite close to the drive systems topic, design and control of grid side voltage under unbalanced grid connected mode with PMFC based WEC. So you are looking at the grid side converter, and what we have discussed actually the machine side or generator side converter. So that FOC technique that we have discussed for motor, it can be used to the generator. Only difference is that now speed command comes from maximum power point tracking, MPPT, of your wind turbine, and the current IQ current is negative, and ID current is also negative if you have if you are operating with an IPMSC. But if it is a surface type, ID is 0 and IQ is negative. Only that's the difference actually. The wind generator control and the PM motor control. Okay. Yeah, power quality, optimum demand. So it looks like we have mostly power system, and hopefully you have learned something very which is not you are not studying about. Okay, I think yes. So we'll come back at 3:30. Right. Thank you for your sharing your topics with us. What's the time now?
It's already
3 o'clock. It's 3 o'clock. Yes, it's okay. You can play if you are like if you don't want to join us, it's still okay, all right? Like I know you have a little baby and it's too late at night and Friday night today. on top of that. So it's all like, if you're busy and couldn't join it, it's fine. Okay. I
Okay.
will be back.
Okay, thank
I'll be back.
I may join you. Okay, I don't want to miss this, so I may join you because the baby's already go to sleep.
Sleep. Okay. All right then. Okay. So see you then at 3:30. You will just leave and then join back at
Yep.
3:30.
Yeah.
Yeah. Okay. Thank you.
Thank you. Bye bye.
Bye.
So participant, please there is a tea break. You can take tea outside. वो शेयर करना है हाँ
इसको बात करने के लिए
Let night का water bottle lecture
लाल चंगाई तो कितना ऐसे दिख रहा
इसका ऊपर जो ये लीड
पूछ रहे हैं
उसका पास होगा वो खुल गया एक खुल गया ये तो वो से
ऊपर तक नहीं
हैं
ऊपर तक नहीं
그다
मेरा
이거 옆에다 그냥 스탠바이가 원도 꼭 나요 মানে স্ট্যান্ডবাই থাকো মানে জিনিসটা বুঝছ না লাইনও ইয়ে আছে লাইন অন করা ফিডব্যাক ইয়ে হইছে আর কি হয় কেন এখন দেখতে আমি তুমি ক্লাসত কে পাছে তোমার তো ওটা নেসার দি পাঠাইতে পারবে আমি একটা
Ramaji, ready? Start mail is opened up.
Yes, madam. Here it is open.
Okay. Then I am sending one document. Just download it.
Session is just now completed.
Yeah, I know.
तो ये फैन क्यों नहीं दिया है गरम लगा है फैन चालू करो ना
Just take the other water.
Ma'am, ma'am, sir, 1 minute you stand. Yes. Ma'am, once you see there in TV also, sir is visible. बाकी तो नहीं है अभी ये 4-5 क्या है कैसा है नो नो జ్యోతి ఇప్పుడు పొద్దున్న 6-7 సర్టిఫికెట్లు ఇచ్చాను కదా
అందులో ఇది ఉంది
ఉంది కదా యువర్ నేమ్ ఆల్సో దేర్ no no it is decided by sir it is not decided by me
not by
sir today ma'am it is coming ma'am
Can you come within 10 minutes? Huh?
I'll say.
yes sir here it is coming yes, sir.
No, voice is out now.
अभी एग्जाम में हो गया सर
आज एग्जाम नहीं हुआ मैडम कल घुसा गया कि इसका टाइम में हमारा तो 15 दिन हुआ था ना वो टाइम में उसको सुनाई दे दिया कल घुसा हुआ सुबह करके बताया कि लोग जगह में अभी सबके साथ
चलिए हम लोग
if you go now.
You see that I'm induction of it. Both electrostatic and electrolytic induction. All Asian people. We are energized, so we are left. With smart technology, smart ideas. Therefore, smart man is there. Well, CJ Gupta, his brain is something like, how super. So,
उधर उधर वो लोग भी बात करेंगे सर।
can you hear me?
Subha, I'm here.
Yes, you can hear me, right?
Yes, Sunil.
So please,
Hello.
can you hear me?
Sir, sound बहुत कम आ रहा है.
Can you hear me?
No, even sound is less.
So please,
Yes, sir.
is it available?
No, very slow.
I'm going to your side.
Hello.
Can you hear me?
Hello. No sound ज़्यादा बढ़ा दो. Madam, can you hear us? Hello. Madam.
Yes, I can hear you.
Yeah, I can also hear you. Sound is bit slow, but that's fine. Not an issue. Yeah. Okay. हाँ?
ऑनलाइन प्लेटफॉर्म में जो है ना,
हाँ. Hello. Hello.
Ramaji, can you hear us?
Yeah, it is still quite low, madam.
Abhi?
No, same, quite low.
Okay. No?
Hello. हाँ, madam, tell me. Oh, still low.
Can you hear us?
Hello.
Yeah, can you hear?
Yeah, you are audible, sir, but very low.
Oh, okay.
Ramaji, can you hear us?
Hello, madam.
Can you hear us?
No, the voice is a little bit changed. Means low to high, but not yet that much high.
Can you hear some echo or it's not? Okay,
Now it is coming, madam, but still low.
Okay.
Yeah, now it is working, madam, little bit. Yes, yes. No, your voice is very low, sir. Very low.
Hello?
Yes, madam.
Okay, come in, sir. Come.
Thank you, sir.
Hello.
Sir.
So can you hear me?
Can you come here? Sir, if you can manage from there, can you come here?
No, your voice is coming so faint.
Sir, can you come here? Physically, actually, if you can manage sign, this if you can come, then we'll be very happy.
Okay. So I understand you are in the auditorium.
Yes, sir.
Acha, okay, I'm coming there. Maybe within 5 to 10 minutes maximum.
Okay, sir.
Okay, bye.
You need to see the problem. What is the problem? Yes. Problem आ गया है।
ये आज ऐसे क्यों हो रहा है बता दो, उस दिन तो अच्छा चल रहा था। पूरा एक्चुअली ये स्पीकर को गेट कर रहा है, इसका वॉल्यूम ज्यादा हो गया। अब सिस्टम का वॉल्यूम बढ़ा, स्पीकर का वॉल्यूम
क्योंकि साउंड को थोड़ा कम कर, साउंड को वॉल्यूम को कम कर।
वॉल्यूम भी ज्यादा है,
वॉल्यूम ज्यादा थोड़ा और ऊपर से ना थोड़ा ज्यादा।
प्रदीप तुम स्पीकर है, वॉल्यूम कम
ये तो बड़ा वॉल्यूम लग जाता है। देखो वो ऑल विदाउट
अच्छा এখন শেয়ার বাড়াবো লাগিব क्या শেয়ার এখন আছে নাকি আছে আছে now you try hello और भी वॉल्यूम का यहाँ तो ठीक है वॉल्यूम
Yeah.
Hello. 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 Hello, Marasi.
Yeah, I can clearly hear your voice, Professor voice. Yeah, Satish.
Yeah. Now your voice is clearly audible, sir.
Yes. Your voice is also clear.
Yeah, my voice is audible to you.
Yes, your voice is audible. Yes.
Yeah, fine.
ठीक आ रहा है तो कैम के वैसे वो
যেটা করবে এটা আর্কিটেক্ট সিরিজ কমাই দিও আমার এখানে ইনপুট কোড এটা একদম
ঠিক আছে
আমি কিতাব ভলিউম কমাইলে আমার এটা ভিডিও
না এটা ওকে আর না
আমার এটা লাইন করতে আছে আমার ভলিউম চলে দাদা পুরো অনলাইন চললো ভলিউমটা একটু কমা ভলিউম ট্রাফিক করে না ভলিউম কম করে দিয়ে দিতে
দাদা এটা ওকে না
Now it's okay.
That's not it's okay.
No, there is Subhash.
Yes, almost calling you. Let them come inside.
Here it's okay now. Audience from the other side.
So what they're
other
saying is
people
the
pay.
voice what they're receiving is very less.
Yes.
Oh, but when other
That is the
people
problem. Slowly they're
pay,
trying to.
it becomes too much of loud.
It will be checked. The gain of the laptop. So overall context laptop. Which laptop it is connected with this what do you call this mic? This one. Yes. ना ये नहीं उसमें वो मास्टर माइक उसका बढ़ाओ মাইকের সারিটা হলো মেইন মাস্টার ওটার মধ্যে কমাইতে পারে না ওরা মাইকের সেটিংটা দেখো ওইটাই মাইকের সেটিং
Now.
আমার
Yes, sir. Thank you, it's done.
তারপর দেখি আমি বলি স্টুডেন্ট বলে কি স্যার মাইকের গেইন বাড়াতে
So now it's done.
Yeah, madam, Dr. Clay is there.
Yeah, good afternoon. Thank you.
So can you start?
Yes,
So it's very pleasant to be able to honor our presence here. Today we have gathered here for taking part in the validity ceremony of the GIAN course titled Advanced Permanent Magnet Machine Drive Technologies for Transport Electrification and Renewable under the aegis of Global Initiative of Academic Networks and Initiative of Ministry of Education, Government of India, at NIT Silchar, organized by the Department of Electrical Engineering from 21st March 2022 to 27th March 2022 after its successful completion. For starting the validity ceremony procedures, first of all, I would like to welcome all the distinguished dignitaries present here physically to the exercise. I request the distinguished dignitaries, our Honorable Director, sir, of NIT Silchar, Professor Shivaji Bandhapadia, sir, and the Chief Guest of today's validity ceremony to the exercise. Now I request Professor S. Vaishya, sir, Dean Research and Consultancy, NIT Silchar, to please the exercise. Now I request Professor P.K. Patawale, sir, Professor Department of Mechanical Engineering, NIT Silchar, and GIAN Local Coordinator to the exercise. Now I request Professor Nidhu Sinha, sir, Professor of Department of Electrical Engineering, NIT Silchar, to the exercise. Thank you, sir. Now I request Professor V.K. Roy, sir, Professor Department of Electrical Engineering, NIT Silchar, to the exercise. Now I request our head of the department, J.P. Mishra, sir, to please come to the dais and raise the dais. Now, I would like to welcome the distinguished dignitary present virtually to grace the dais. I request the distinguished dignitary, Dr. Rukmini Datta Ma'am, Associate Professor, Energy System Research Group, School of Electrical Engineering and Telecommunications, University of North South Wales, UNSW, Sydney, Australia, and the foreign expert of this GIAN course to grace the dais. Thank you, ma'am. Now, on behalf of the Department of Electrical Engineering and Silchar, I welcome you all, and I would like to express my heartfelt gratitude for your presence in this valedictory ceremony of the 5-day GIAN course on Advanced Permanent Magnet Machine Drive Technologies for Transport Electrification and Renewable Energy, organized by the Department of Electrical Engineering and Silchar. Once again, I would like to extend a warm welcome to all the dignitaries, deans, head of the departments, faculty members, students, and all the participants present here, both physically and virtually. Now, with the permission of the chief guest of today's valedictory ceremony and the director of NIT Silchar, we are going to felicitate the guests present physically on the dais. Now, I request Dr. L.C. Silchar, sir, the course coordinator, to felicitate our honorable director, NIT Silchar, Professor Shivaji Chandra sir, and the chief guest of today's valedictory ceremony. Welcome, sir. Now, I request Dr. Dulal Chandra sir, Assistant Professor, Department of Electrical Engineering and NIT Silchar, to felicitate Professor S. Vaishya sir, Dean RNC. Now, I request Dr. Rajiv Dey sir, Assistant Professor, Department of Electrical Engineering and NIT Silchar, to felicitate Professor P.K. Patawari sir, Professor, Department of Mechanical Engineering and NIT Silchar, and GIAN local coordinator. Thank you, sir. Now, I request Dr. Srijit S., Assistant Professor, Department of Electrical Engineering and NIT Silchar, to felicitate Professor Vijay Sinha sir, Professor, Department of Electrical Engineering and NIT Silchar. Thank you, sir. Now, I request Dr. Rajkumar Vishwa sir, Assistant Professor, Department of Electrical Engineering and NIT Silchar, to felicitate Professor B.K. Roy sir, Professor, Department of Electrical Engineering and NIT Silchar. Thank you, sir. Now, I request Dr. Sahebi Dey, Assistant Professor, Department of Electrical Engineering and NIT Silchar, to felicitate our HOD, Dr. Gabriel Mishra sir. Now, I request Tapan Pradhan sir, Assistant Professor, Department of Electrical Engineering and NIT Silchar. Now, NIT Silchar, on behalf of Department of Electrical Engineering, is going to felicitate the dignitary present virtually on the dais. Now, NIT Silchar fraternity is felicitating Dr. Rukmini Datta Madam, Associate Professor, Energy System Research Group, School of Electrical Engineering and Telecommunications, University of North South Wales, UNSW, Sydney, Australia, and the foreign expert of the GIAN course. Now, I request Dr. L.C. Silchar sir, course coordinator of the GIAN course, to present the report of the course.
A very good afternoon to one and all present here. At the same time, good afternoon to Professor Rukmini Datta, Dr. K. who are now in Sydney, Australia. Honorable Director and NIT Silchar, Professor Shivaji Bandyopadhyay, Local GIAN Coordinator, Professor P.K. Patwari, the HOD of Electrical Engineering Department, Dr. J.P. Mishra, the Dean Research and Consultancy, Professor S. Boyso, Professor Nidhu Sinha, Senior Faculty, Power and Energy Research Group, Professor B.K. Roy, Senior Faculty, Control System Research Group, Electrical Engineering Department, the external faculty of the GIAN course, Dr. Rukmi Datta, Dr. Clay So, my faculty colleague, the participants, and ladies and gentlemen, I hereby welcome all of you to this validatory function of this GIAN course. Now I am presenting the report of this 5-day GIAN course. The primary objectives of this GIAN course were as follows. Number one, they expose participants to the fundamentals of permanent magnet machines and drive technologies, build confidence and capability among the participants in the industrial adaptation of permanent magnet machines and drive technology, and provide guidance for troubleshooting in the design and control of PM machines drive system. Number two, provide exposures to practical problems and their solutions through case studies in the design and control of permanent magnet machines. Enhance the capability of participants to design and control of permanent magnet machines applicable to emerging technologies. To fulfill these primary objectives, the course was designed for 12 hours lecture class and 8 hours tutorial classes by faculty Dr. Rukmi Datta, Associate Professor, School of Electrical Engineering and Telecommunication, University of New South Wales, Sydney, Australia. 10 hours of lecture class and 8 hours of tutorial classes were taken by Dr. Rukmi Datta. 2 hours of lecture classes were taken by Dr. L.C. Silchar, course coordinator of this course. Dr. Rukmi Datta was assisted by Dr. K.S.U. in the tutorial classes. 51 participants had registered for this course, out of which 4 faculty members, 4 are BTech students, 43 numbers are MTech and PhD students from various academic institutions of in India, including NIT Silchar. The day-wise activities of this function of this 5-day course are as follows. First day, the inaugural ceremony was held at 9 a.m. on 21st March 2022. Honorable Director NIT Silchar was chief guest of that function. The external faculty Dr. Rukmi Datta, local GIAN coordinator Professor P.K. Patwari, Dean Academy Professor A.K. Barbhuyan, Dean RC Professor S. Boyso, HOD of Electrical Engineering Department Dr. J.P. Mishra was present in the meeting. All the participants and other gentlemen were also present in the meeting. So the participants and other guests from NIT Silchar attended the function physically, and the foreign faculty and participants outside NIT Silchar were online. Dr. Rukmi Datta briefly outlined the possibilities of collaborative research, the use of world-class laboratory available in UNSW and NIT Silchar. After the inaugural ceremony, the technical session began. The first 2 lectures was taken by Dr. Rukmi Datta, Dr. talk about the electric vehicles drives and renewable conversion challenges. The possibilities of research in these emerging areas was also highlighted. Dr. Soikia had taken 2 lecture classes after the last week. Dr. Soikia had delivered his lecture on a refresher of electromagnetics. The lecture class was followed by quiz 1 of 10 marks of 20 minutes. On the same day, quiz 1 was evaluated. On the day 2, lecture number 5 and 6 was taken in the first half. Dr. Rukmi Dutta had clearly explained the permanent magnet machines, starting from basic principle to the design. Dr. Klesu, a postdoctoral research fellow under Dr. Rukmi Dutta, was also a resource person along with the Dr. Rukmi Dutta in tutorial class 1. They have taken 2 hours of tutorial classes on a brief review of machine fundamentals. The quiz 2 session was also taken at the end of the tutorial class and it was evaluated. Lecture 7 and 8 was taken by Dr. Dutta. She had explained the race part of the permanent magnet machines. The design aspects of permanent magnet machines are clearly demonstrated. Dr. Clay Su, along with Dr. Rukmi Dutta, had taken the tutorial class 2 on the 3rd day. Dr. Clay demonstrated tutorials on the machine design fundamentals and introduced FEA. The quiz session 3 was also completed on the 3rd day. Day 4, lecture number 9 and 10 was taken by Dr. Dutta. This 2 hours lecture, in this 2 hours lecture, DQ model of controlling the permanent magnet machines, field-oriented control or vector control have been described in details. Dr. Clay had taken a tutorial class of 2 hours on PMSM, drive fundamentals in Simulink using FEA. The tutorial class was followed by quiz 4. On the day 5, that is today, Dr. had covered the design of permanent magnet machine design. A tutorial class of 2 hours of machine performance was taken by Dr. Clay in the second half. Dr. Rukmi Dutta also present in the tutorial class, and the quiz was not taken today. We have considered 4 quiz only. The conclusion of this course is like this. The course is really interesting. The primary objective of course have been fulfilled today. I am sure that participants of this course will definitely go for research in permanent magnet machines, mainly the interior type permanent magnet machines and its control using various software tools. The secondary objective of this course are also partially fulfilled. There are many secondary objectives of this GIAN course. One such outcome is the collaboration opportunity. Already NIT Silchar had conducted a meeting on 11 March 2022 with the foreign faculty to explore the collaboration opportunity and research between this NIT Silchar and New South Wales. It was explored that there are many scopes in this regard in future, and it will be done in future. Also, I hope electrical engineering department will have move towards the design-oriented research along with the application-oriented after this course. A certificate along with a grade sheet will be issued to all the participants. This course carries 1 credit and institute-wise that can be taken in our institute. As per our institute rule, this will be reflected in our participants' mark sheet as a audit course. So with this source, I conclude the reports of this GIAN course. Thank you.
Thank you, sir. Now, I would like to request our Honorable Director, NIT Silchar, Professor Shivaji Bandyopadhyay sir, and the Chief Guest of today's ceremony to deliver his address.
Very good afternoon to Dr. Rukmi Dotto, International Faculty of the GIAN course on Advanced Permanent Magnetic Machine, Drive Technologies for Transport, Electrification and Renewable Energy. We started on 21st and today is 25th. And much before that, in order to fulfill the objectives of the GIAN course, we had an interaction meeting with Dr. Dotto also and our colleagues from NIT Silchar. So that in the future collaborations and collaborative research activities in the related domain, so that can be started. I think during the period of the GIAN program also, so there are a lot of discussions and deliberations, and we wish that the participants from NIT Silchar, as well as the participants from the other places, so they must have identified the future research areas that needs to be taken care of. And from the say the demonstration or going through that is what are the different tools or the systems of the drive that have been developed at University of North South Wales. So obviously all the participants have got the idea, and during these days of the GIAN program also, there is the kind of work that are done at the University of North South Wales, so that not only in the simulation, but they have more trust on the development strategies as well. And I wish that all the participants, they will find that those who work in this area, so they will try to be there at the university and work with Dr. Dotto and her team. And the other objectives, that is the GIAN course, normally when it is held in the physical mode, that gives you ample scope for the networking also. Networking not only with the resource persons, but also among the participants as well. So this is something which goes missing to some extent in an hybrid mode, but in order to compensate for that, so yesterday we had a social function, and where the participants also who are not in the campus itself, they got an opportunity to interact during that social event. I think these are the ways, and at the same time, there is the idea of the audit course, so that at least there is a mention that is if the students they take part, participate in this course, it is not only that is for their future career, those who want to pursue research or say the teaching in this domain. So the certificate obviously will be helpful for that part, but also at the same time having one credit, say one audit course, because audit with one credit actually say does not mean anything. But obviously in future, because sometimes say the formal regulations actually put a bar on what you can do, but with the flexibility that the national education policy has given us, I think very soon we'll be able to see that. That is, whenever there are courses, there are evaluation mechanisms. So based on the number of hours that you pursue on that course, so you get a credit point, and so all the formalities say are taken care of. So in future, so that will be more beneficial, not only for the participants from the host institute, but also participants from other participating institutions as well. And in future, there will be more and more GIAN programs also, and all these GIAN programs will, past also we have seen that they have been extended to collaborative activities at different levels. And in future, GIAN programs will also be working towards that aspect. So with this, I wish the GIAN program has been successful, and the future deliberations will be even more brighter for this program. Thank you. Okay, thank you. I have another program.
Thank you, sir, for being present here with us today. Now I request Dr. Rukmi Dada, ma'am, Associate Professor, Energy System Research Group, School of Electrical Engineering and Telecommunications, University of New South Wales, Australia, and the foreign expert of this GIAN course to deliver her address.
Hello, can you hear me?
Yes, ma'am. Voice is a bit shaky.
Is it okay?
Yes, ma'am, it's better.
Okay. First of all, good afternoon to everyone. And I also want to congratulate a participant for completing the course. It would not have been possible without obvious support from NIT Silchar and GIAN. So I thank Government of India for providing this opportunity to have deliver this course to you and to begin something more than just a course, a more stronger collaboration between institutes. I also thank Dr. Silchar for giving us this opportunity to conduct this course, and I encourage strongly the participant to think big. If you work hard and if you're motivated, anyone can actually do or contribute significantly in nowadays in the global field. I have a very similar background like yours. I did my engineering from an institute like yours, and then I was able to come out and be able to contribute to a research field that I like. Similarly, one day you will also be able to do that. Maybe in the beginning there could be struggles, but if you do not give up and keep working hard, it could be, it is always possible to do things that you like, research or like being an engineer where and in a job that you like. So for me, this is like this job, which I really love because it allows me to do work that or do research that I like. And that's the beauty of having this independence, academic independence. We could go to industry and do jobs, but then in the industry job, usually it is the industry who decides what the work you are going to do. But in the academic field, it is like you can do or you can research the things that you like, and no one is pressuring you to do something that is may not be of your interest. So being academic is in that way really a job that you can enjoy. But of course, then there is you also have, along with it comes the other maybe pressure of that's like getting grants, making your PhD students good enough to stand in the world stage. But that's something you have to, some price that you have to pay. I definitely encourage also all of you, including my colleagues at NIT, to look for opportunities in the area of Australia, India strategic research collaboration funds. So there's some events you may be able to, or together we may be able to apply those sort of funds, and that can help to make this collaboration grow further. That's all from my side. It's a very long day for me. It's nearly 9:30 p.m. At night, so almost 12 hours at work today. I haven't prepared a long speech. That's all from my side. Thank you very much.
Thank you, madam, for being present here with us for the valedictory ceremony, and also for your kind words, and also for the excellent sessions delivered during these days. Thank you so much, ma'am. Now I request Dr. Clay Chu, Postdoctoral Research Associate, UNSW Australia, to share his words with us.
Okay, hello everyone. Thanks for listening to my tutorials, and also I want to say a big congratulations to all of you for completing this course. This is a very wonderful experience for me because I delivered the tutorial, but I am learning from doing this tutorial, and I'm also learning from every one of you. Yes, like I said, I've met many talented Indian engineers and students at UNSW, and I know many of you are very talented and you are special expert in your field. So yeah, this is just one course that I happen to be your tutor, but I hope in the future we can work together, we can work as colleagues, and I will learn from you. And I hope one day we can meet in person here in Sydney or in India. And when you come to UNSW, please let me know. I will buy you a cup of coffee and I will give you a tour to our lab. Okay, so yes, big thank you to all of you. Keep in touch. That's all from me.
Thank you, Dr. Clay. I request Professor P.K. Patawari, sir, Professor Department of Mechanical Engineering, Electrification and Renewable for the
Thank you, madam. Very good afternoon, respected director, sir, who has present a few minutes back physically here. Professor B.K. Rai, Professor Vaishyo, Professor Nidhi, Dr. J.P. Mishra, Dr. Silchar, my other colleagues, student friends and participants. It's indeed a great moment for us and very joyous feeling that one more course in the institute is being completed very successfully. This is the first course in phase 3 and in totality 18th course in the institute. So one more feather in the cap of the institute. So for that, I would like to thank first Dr. Silchar for bringing this course and the entire electrical engineering department. Indeed, I am very much thankful to all the participants. Because of you only, it was possible to have this course, because we have our expert, Dr. Rukmi Datto. She has also supported us. So thank you, Madam Datto, for accepting our invitation and conducting this course very successfully. And I believe that our participants get immensely benefited by this course. So in this regard, we are very much thankful to the Ministry of Education, the Shiksha Mantralaya, and the National Coordinator GIAN for giving us this course so that it is realized here in this institute. Today, we are celebrating the completion of the course. This is one of the aspects. That is the formal teaching learning process in the classroom is being completed, but it is again opening up the new path for the collaboration. As you know that GIAN says that it's a global initiative for academic networking, and that networking, it will never be going to be finished and will not have any validity for that networking, and it will remain continue forever till we give our efforts. So
we require the support of Dr. Rukmi Dotto. I believe she will always be kind enough to support us, and whatever the kind of help we require, she will always extend the love and affection to this institute as a to department. And for the participant, I say that now today onwards, you are going to be the direct student of Dr. Rukmi Dotto, and that bonding has been created through this course. So now onwards, whenever a student asks a teacher, the teacher never denied. So we believe Dr. Rukmi Dotto will be kind enough to support the participants in every respect in their academic life in future, so that the bonding will be much stronger in future. So with this, I am very happy, and I thank all of you for being with us, and best wishes. Thank you.
Thank you, sir, for your kind words, kind and motivational words. Now I request Professor S. Vaishya, sir, the Research and Consultancy and IT Silchar to deliver his address.
A very good afternoon to all. Professor Roy, Professor Patori, Professor Sinha, Dr. J.P. Mishra, my other colleagues, Dr. Shunkia, the coordinator of this course, participants, online as well as offline, and more importantly, our international expert faculty, Dr. Rukmi Dutta. 5 days ago, we assembled here for inauguration, starting of this course, and today we are feeling farewell to you. As per the report presented by the coordinator, these 5 days were really hectic and a lot of things were delivered. We are thankful to the international expert for sharing her knowledge and training our participants, who are primarily our research scholars, PG students. And as our local coordinator, Professor Patori, pointed out, definitely a solid networking has been established, and it was mentioned in the inauguration program also. Before starting the program, this networking was established, so it is really encouraging for us. We are thankful to the expert, Dr. Doctor, for that she has spared her time. And of course, we could not get her physically because of various constraints. But I believe, since she is from Assam, whenever she visits Assam, if she can be kind enough to visit Silchar, then we can get more benefits of this networking. So far as the participants are concerned, you all are mature. We are not supposed to advise you. But one thing I always tell students, that teaching and learning are two different things. Teaching, it is the responsibility of the experts. But the learning, no one can learn for us. We need to learn ourselves. That we need to keep in mind. So it is not that after this, attending these 5 days, all these lectures, you have become master. It is also not possible. But if this minds of some of you could be ignited, then you can carry forward, learn it further, and take up the innovative research in this emerging area. That will really be very good for your future career and also for the institute as a whole. So I wish all the best to all the participants. Thank you.
Thank you, sir, for your kind and inspiring words. Now I request Professor Nidhu Sinha, sir, Professor Department of Electrical Engineering and Medicine, to deliver his address.
Very good afternoon. Dr. Rukmi Dutta, external experts, and our associate, Dr. K, and Professor Bushra, DRNC, Professor Patwari, Coordinator, GIAN Program, Professor D.K. Rai, and Dr. J.P. Misra, and Dr. S. Selkia, Coordinator of the program, colleagues, and dear participants. At the outset, I'd like to congratulate Dr. Selkia and his team for wonderfully completing a very wonderful program that was on a topic which is very, very prominent and futuristic one. And I think that all the participants might have been sensitized with the advanced permanent magnet, specifically that super permanent magnet machine drive technologies, which is mean for that transport, electrification, and renewable energy. So I feel that being that experts, external experts, who happens to be that dwelling in this technology, where India it is not much, flourishing. Because of that, we have limited developments in the material science domain. So hope that expert being from Assam and very much aware about the problems faced by that northeastern region, and hope that these will open up that avenues for a lot more explorations for coming up with the societal problems, burning problems related to the transportation, right from micro level or pico level to the macro level. At the same time, coming up with that renewable energy, that also from the pico level to the macro. Macro, I won't give much more specifically for the northeastern side. It is the micro level or pico level generation is very much important. Where that when you integrate with your super magnet, permanent magnet technologies together with the DLDC machines, and hope that it will open up that probably that our external expert, the right person, to be acting as a very, very shows and that which is inspiring, shows being also young and dynamic, and hope that this will mark as a beginning for a new era where this electrical department with the active association of the external experts will come up with a lot more projects which will have direct impact on the society. And only then I think that we will see that in future coming days means what personally we also I feel that okay, yes, at least something is done at the end of that. And I'm very much thankful that external expert given their efforts for that association with that. And at the same time is what our PhD scholars who will after getting the PhD degree will dwell in the real life situation, will take up that issues there. And with that, I congratulate Dr. Selkia and his team for such wonderful completion of this program. And at the same time, I'd like to thank the external experts for making this happen today. Thank you all.
Thank you, sir, for your kind and motivation words. Now I request Professor D.K. Roy, sir, Professor Department of Electrical Engineering and Energy System to deliver this address.
So very good evening to all of you present here. My colleague, Professor Patwari, Professor Vaishya, Professor Nidusina, Professor J.P. Misra, Coordinator Alexis Shekia, I could see many more colleagues here. And on the other side, Madam Datta and his PhD scholar, his postdoc scholar, Dr. Pachu. And my dear participant for this GIAN course. So far the report that we have received, the course was successful. As it is been narrated by most of the speaker, this is the first part of teaching learning. Madam has given everything, whatever she had. You have taken to some extent whatever you could. But friends, that is just the starting. Those who got motivated in these particular directions, and also it has been said by Mr. Nidhu Singh very specifically, there is a plenty of scope in our country to work on this particular field. So therefore, if those who have taken this particular topic for your future endeavor, please know, friend, there is no alternative to hard work. Please remember that. This is my request to all the participants. You can only achieve to your target whatever intellectual capability you have, whatever other capability you have, but along with all these, you must have a zeal to do that hard work. Therefore, I wish whatever you have gathered during the last 5 days, you will continue your work, and then maybe after a gap of 1 year, 2 years, you will see that we will start getting fruits out of it in the form of some conference paper, some journal paper, and finally, we will see some real collaboration between Madam's group and groups in India. In the whole process, whatever Madam has given to you, she deserves a big applause of thanks. So, all those things could happen because Silchar from our side had managed everything so nicely for you. So big thanks to Dr. Silchar also. And outcome of these GIAN courses are measured not at this particular end, but will be measured at a later part when, as I say, those outcomes like papers, patent, actual collaborations, further project will come out. And I expect and we wish that we will see some such outcome in near future. With this, let me conclude. Thank you. Thank you very much.
Thank you, sir, for your kind and motivation words. Now I request Dr. J.P. Mishra, Head of the Department of Electrical Engineering and IT Systems, to deliver his address.
A very good afternoon to everyone, and also a very good evening to Madam Rukmi Datta and Dr. Clay Chu from Australia. It's my pleasure to welcome all the dignitaries on the physical as well as virtual dais of this valedictory ceremony of the GIAN course, that is Advanced Permanent Magnet Machine Drive Technology for Transport, Electrification and Renewable Energy, organized by the Department of Electrical Engineering, NIT Silchar, under initiative of Ministry of Education, Government of India. Honorable Chief Guest, Professor Sibaji Bandyopadhyay, Director NIT Silchar, who is now not present. He has already delivered his valedictory address. Honorable guest and foreign expert of the GIAN course, Dr. Rukmi Datta, Associate Professor of Energy System Research Group in the School of Electrical Engineering and Telecommunication at University of New South Wales, Sydney, Australia. Respected Dean Research and respected local Respected Professor, Senior Professor, Power System Research Group of Electrical Engineering Department and Silchar. Respected Professor B.K. Roy, Senior Professor, Control System Research Group of Electrical Engineering Department and Silchar. Dr. L.C. Saikia, the coordinator of the course. Esteemed faculty colleagues, dear participants from the academia, industry, and research laboratories all across India. I, on behalf of Department of Electrical Engineering and Agriculture, would like to thank all the dignitaries and participants for joining this valedictory ceremony. As mentioned by the coordinator, there are almost 60 registered participants who have actively participated during the deliberation of to make this GIAN course a successful event. We are thankful to our foreign expert, Dr. Rukmi Datta, for delivering talks with her intense expertise to make this program more interesting and informative. A broad spectrum has been covered through this GIAN course, which highlighted the necessary technological advancement in the field of industrial motor drive system, mainly the applications of permanent magnet machines in the newly proposed transport electrification and renewable energy systems. The main topic covers are fundamentals of permanent magnet machine drive system, and analytical DQ modeling, based design methods and analysis, finite element analysis based design methods, design challenges for emerging applications such as electric vehicles, wind energy conversion, recent advances in permanent magnet machine design, and future challenges. Hope this GIAN course has provided unique opportunities and a platform for the participants in getting exposure on new developments and advances in permanent magnet machines and drive technology, for doing any collaborative research work in the newly proposed transport electrification and renewable energy field of applications for the sustainable development. Lastly, we appreciate the tireless effort of the coordinator, Dr. L.C. Saikia, and his entire team, and congratulate them on the successful completion of this GIAN course. We must also look forward for our future course of action for doing any collaborative research work in the newly proposed transport, electrification, and renewable energy field of applications between the Energy System Research Group of School of Electrical Engineering and Telecommunications at University of New South Wales, Sydney, Australia, and Electrical Engineering Department and Agriculture through the initiative of conducting different possible faculty and student exchange programs. Thank you all again.
Thank you, sir. Thank you for your kind words. Now, with the permission of the dignitaries present here, I would like to request Dr. Tapan Pradhan, sir, Assistant Professor, Department of Electrical Engineering and Silchar, to felicitate Dr. L.C. Saikia, sir, coordinator of the GIAN course. Thank you, Tapan, sir. Now, I would like to request the participants of the GIAN course who are physically present here to kindly share your valuable feedback about this 5-day program.
Respected dignitary, present over the dais, of the dais, and present in virtual mode. I, Manoj Bera, research scholar, Department of Electrical Engineering, NIT Silchar, like to thank Dr. L.C. Saikia, course coordinator of this GIAN course, HOD, and the professor of the department to organize such a nice course, GIAN course for us, that is entitled of Advanced Permanent Magnet Machine Technology for Transportation and Renewable Energy. I want to thank Professor Rukmi Datta, expert of this GIAN course, presently working as an associate professor in Energy System Research Group, School of Electrical Engineering and Telecommunication, University of New South Wales, Sydney, for such an excellent informative talk during these 5 days of this course, where we learn from the Datta introduction to electric vehicle drive and renewable energy conversion challenges, permanent magnet machine, control of permanent magnet machine, design and performance of permanent magnet synchronous machine. I also would like to thank Dr. Clay Chu, postdoctoral fellow, UNSW, Sydney, for such a comprehensive tutorial session on machine design fundamentals, permanent magnet synchronous machine drive fundamentals in Simulink, and PSM designing ANSYS Maxwell FEA software. In my view, as in my graduate curriculum, in machine 2, I studied there is a special machine that is stepper model, reluctance model, that is, but there I hardly studied about this permanent magnet machine. But overall, in this course, I learned fundamental of three-phase electrical machine, permanent magnet material, types of permanent magnet materials, and their work principle, analytical design, model and analysis of electromagnetic performance, and their designing the finite element analysis, and the DQ theory and DQ model of permanent magnet machine, and the fundamental of permanent magnet machine, and their control. In the last, I would say, as a research scholar of this department, my colleagues are working on the microgrid control, controlling the power system, level of the design of the level of converter, control for the charging station. But this design aspect of the machine, which required by the wind generation in the today days, and is also electric vehicle, is still now not explored in our department. And also this design in the ANSYS software. This ANSYS software, I would like to say this ANSYS software license is already held by in the institute in the mechanical department. But as I mentioned by the Dr. Clay Chu, this software having two different tools. But in our electrical department, the electromagnetic tool, that is Maxwell 2D, 3D license is required in order to implement this machine design in the research. So I hope this definitely this GIAN course will help us to go in a different way, so that with this outcome we can come up with obligations which will help in the future in order to implement the electrical vehicle concept, which is new and which is promoted by our government to IC, which replace the IC engine. And with this, in the last, I would like to thank you, ma'am, for your spacious time to give us, to educate us in this topic. And I also like to thank Dr. Clay Chu. Thank you. Thank you.
Thank you, Manoj. Any other participants would like to say something?
Respected dignitaries of the dais and on the dais and in virtual mode. I am Devashish Kumar Patel, PhD scholar from Electrical Engineering NIT Silchar. I am giving heartfelt thank you to the GIAN course coordinator team and for organizing such a wonderful course for students. And special thank you to Dr. Rukmi ma'am and Dr. Clay sir for beautifully present the advanced solar magnet and its use in the transport electrifications like electric vehicle. And at last, the course was beautifully designed from the basic fundamental of advanced solar magnet to its practical implementation in electrical engineering in more detailed and in-depth manner, which encourages us to do research in this advanced state. Thank you. At last, I request Ma'am and Clay sir to give the future direction in our research and keep our hand in our future. Thank you.
Thank you, Devasis. We also would like to hear from the participants who are virtually present here. Anyone would like to share their views? Yeah, so any participants who are in the virtual mode would like to give the feedback? So then thank you everyone for sharing your valuable feedback about the course. This will surely motivate us and help us to improve further. Now, I would like to request Professor P.K. Patwari sir, Professor Department of Mechanical Engineering and IT Silchar and the Global GIAN Coordinator to distribute the certificates to the faculties who were participants of this GIAN. I'd like to request Dr. Gulal Chandra sir, Assistant Professor, Department of Electrical Engineering, to come and collect the certificate. Thank you, sir. Now, I would like to request Dr. Srijit S., Assistant Professor, Department of Electrical Engineering, to come and collect this. Thank you, sir. Thank you, Dr. Sir. Now, I would like to request our senior professor, Professor Nidhu Sinha sir, to give away the certificates to the PhD scholars who are present here. Sir, Madam. Thank you, ma'am. Thank you for being present here during the registry ceremony. Yeah, Mostly Buyan. Mr. Amit Kumar. Thank you, sir. Now, I would like to request our Professor P.K. sir to give the certificates to the PG and UG students who are participants of this GIAN course. Mr. Saikil Das. Ms. Manvi Sushma. Mr. Praveen Kumar. Thank you, sir. Now, I would like to request Dr. L.C. Saikya, sir, Associate Professor, Department of Electrical Engineering and IT Silchar, and the course coordinator of the GIAN course to deliver the vote of thanks.
Honorable Director, sir, already sir is busy in some other meeting. The foreign expert, Professor Rukmi Datta, our most valued guest on the dais and of the dais, the participants, my colleagues, ladies and gentlemen. It is my privilege to have asked to propose a vote of thanks on this occasion. I, on behalf of Electrical Engineering Department and the entire NIT Silchar, offer a hearty thanks to all of you. First of all, I am thankful to Almighty for giving us the courage to successfully complete this GIAN course. I extend my hearty vote of thanks to Professor Shivaji Bandyopadhyay for his valuable speech and time, which encouraged us to complete this GIAN course. I also like to thank our Honorable Director, sir, for all-round support to organize this GIAN course. Dr. Rukmi Datta, the foreign expert, has designed this course. She has accepted my request in a single mail for this GIAN course before 2 years. She had taught us the topics of this course given so seriously that I had never seen in other courses that I was attended. The participants got in-depth knowledge on permanent magnet machine types, their control, and their application in EV and renewable energy. She had communicated with me each and every points during last 1 month to make this event a great success. I extend my hearty vote of thanks to you, Madam. Dr. Clay Chu, presently working at an UNSWF as a postdoctoral research associate, have taken all the tutorial class along with Madam. He had clearly demonstrated all tutorial problems related to the fundamentals, designs of permanent magnet machines. I extend my vote of thanks to you, sir. I'd also like to offer my vote of thanks to Professor P.K. Patwari, the local GIAN coordinator, who always advised me for conducting this GIAN course, due to which we have completed this course successfully. I also like to offer my thanks to him for his time and valuable speech at this function. I must mention our deep sense of appreciation to Professor S. Wiso, Professor B.K. Roy, Professor Nidhu Sinha for their valuable speech and time given for this function. Thank you, sir. The HOD of the Electrical Engineering Department, Dr. J.P. Mishra, had always helped me in every aspect to make this course a grand success. Thank you, sir, for your support. I would like to thank Dr. Rajiv De and Dr. Asarani for any time help to conduct this GIAN course. I extend my vote of thanks to both of you, sir. Sir and madam. My colleague Malakar, Raju, Tapan, Swapna, Risa, Ashish, Amitesh, Sriji, Jivandar have anchored the sessions of this GIAN course. I extend my vote of thanks to all of you. I would like to offer my vote of thanks to all the professors and my colleagues, students of Electrical Engineering Department for their presence and valuable advice to make this course a grand success. I extend my vote of thanks to Dr. Naresh Babu, Computer Science Engineering Department and NIT Silchar, Mr. Manos Mohanto, who is working hard for last 7 days to make this program successful. Without participants, it is not possible to conduct this GIAN course. And this valedictory function. I extend my vote of thanks to all of you. I would like to thank our PhD scholars, namely Sotis, Manoj, Sandeep, Alok, Dekaraj, and Mosuri and Jyoti for their all-round support to me to conduct this GIAN course. At last, I extend my vote of thanks to Mr. Shomodip and Mr. Rajat of account section, all the students, faculty members of NIT Silchar, and the ladies and gentlemen present in this valedictory function. With these words, I conclude the vote of thanks for today. Thank you.
Thank you, sir. Now we have come to the closure of this valedictory ceremony of the 5-day GIAN course titled Advanced Permanent Magnet Machine Drive Technologies for Transport, Electrification and Renewable Energy, organized by the Department of Electrical Engineering and NIT Silchar. Once again, thank you all for joining us in this valedictory ceremony. Have a good day. So please join us for the tea.